Once upon a time, there was a point inside a plane. But in fact, this point was not alone. A second one existed, seemingly opposite in every respect. As the 2 points moved around one another, it became clear they were more than mere points. They shaped the space around them, casting regions of light and shadow, a dance of shapes, delightful in its mathematical elegance. Then came a third, partitioning the plane into even more distinct regions. The points, now called sides, formed patterns that came to be known as the Voronoi Diagram. Today, I invite you to walk with me into this world, to explore the strange, precise beauty of Voronoi diagrams. Georgy Feodosievich Voronoi was a Russian mathematician born on April 28, 1868. He was one of the main actors in the study of a specific kind of diagram. These diagrams are called by many different names, but Voronoi diagram is the one I'll be using. A Voronoi diagram is a partition of a space, usually a two-dimensional one, into regions, called cells. Rephrased in a clearer way, what this means is that it is a way of dividing a space into multiple cells. Here is a Voronoi diagram with 10 different cells of varying colors. Hence, here we divide the screen into 10 different regions. In what way exactly we divide the space depends on a set of points scattered around the plane called sites or generators. You can think of them kind of like the nuclei of a biological cell, or an impurity that is used to grow crystals or mold. In fact, simulating growing regions from each of these generators is a way to produce a Voronoi diagram. This also explains why the generators are called this way. A more formal way to define a cell becomes the subsection of a plane that is closest to a given site. For example, the cell whose boundary is highlighted right now is composed of all the pixels of the screen whose site they are closest to is the one in the middle. I mentioned biology several times already, and this is simply because Voronoi diagrams are so prevalent in nature. Anywhere you see growing cells or one that push one another equally, you're almost guaranteed to find Voronoi diagrams. A few examples include turtle shells, giraffes, soap bubbles, honeycomb, or even some tomatoes. That last point is a little different from the rest though. It comes from cells that do not all grow at the same rate, forming curved boundaries, but don't worry, we'll get back to that one in a bit. Voronoi diagrams are both random and organic at the same time, which is why they're often used in computer graphics. To generate realistic terrain or organic textures, one could use cellular noise, also called Voronoi noise. And for a final example, since a cell is composed of the points that are all closest to a given site, they describe regions of control. This is a perfect way of modeling how districting works in a city, for example, showing how power plants or antennae reach parts of the population. It can even be stretched as far as visualizing how predators can rule a section of a forest, for example, and the boundaries of their territory. I could go on for hours, but I think you get my points. Whatever discoveries we make in this video, no matter how abstract they look, could be useful to potentially dozens of real-world applications. But first, I want to motivate what we'll be discussing by showing you a simple way of generating Voronoi diagrams with a computer. All the applications I showed could use a little help from a computer to speed up research, but the technique we'll cover will push that to another level. So let's see what a computer could be doing if it were to display such a diagram on a screen. Here I only kept 3 points to make it clear what we are actually working with, but the reasoning stays the same. With the only information being 3 sites, we want the computer to reconstitute the entire diagram. To render on a screen, we need to find the color of each of its pixels. In the case of a Voronoi diagram, let's say we want to identify the different cells with a color, one per site. To do that, we'll first assign a color to each site. Then for every pixel, we'll have to find which cell it is part of, because that will give us its color. This can be achieved by calculating which site is closest to each pixel, and then color the pixel with the color of that closest site. For example, this pixel here is closest to the site in red, which means it has to be colored red. Repeating the process for every pixel gives us this image, which is an approximation of the real Voronoi diagram we saw earlier. Now we have a problem. With our human eyes, we can clearly notice the cells, and I'll highlight them one by one. But since we created the image one pixel at a time, the computer has no idea what these cells are. And that's a problem because we might want to interpret the data, extract information from its cells, not only display it to a screen. Even then, simply rendering this simple image is very slow for the computer, since it has to do a lot of computations for every single pixel on the screen. In this video, we'll be attempting to solve both these issues by analytically finding the edges and polygons that form the cells. We will use math to find another way to draw Voronoi diagrams, one that is way faster and that offers more possibilities. Through this process, you'll also learn to understand Voronoi diagrams. You will develop a better intuitive understanding of what they look like, how they behave, and their mathematical properties. So let's dive right in. Before we dive into the math, it is important to know exactly what we're trying to achieve. Precisely, we need to find the locations of the vertices and edges that make up the Voronoi polygons. For a given cell, we'll define its polygons vertices as all the intersection points of that cell with two neighboring cells. What I mean by neighboring just means that the two cells must share a side, but we'll go back to this definition later. It is not enough though to just find the polygons points and then link them up in whatever order, because we could end up with degenerate polygons. We need to instead first compute the position of the vertices, then find a way to link them up in the correct order. Let's start by finding out the positions of the vertices. We define them as the intersection point between three cells. Now, for a point to be part of a cell, it has to be closest to its site than any other side by definition. Extending this logic, if a point is equidistant from two separate sites, then it is part of both their cells. In the same way, a point that is at the same distance from three separate sites is part of all their respective cells. It then becomes an intersection point, that is, a vertex of one of the polygons we're trying to build. We just need a way to calculate where this equidistant point is, and we'll have the position of a vertex, half the solution. Let's consider three cells of sites A, B, and C, and an intersection point P that is equidistant from all of them. P is the point we're trying to find the position of, and the locations of all the other points are known. For P to be equidistant from all A, B, and C, it first has to be equidistant from A and B alone. I'll draw the set of points that are equidistant from A and B, and we will know P has to be among them. We can immediately notice that this set of points is a straight line. This line actually has a name, it is called the perpendicular bisector of A and B. But we should not forget that P is also equidistant from A and C by definition. So let's also draw the perpendicular bisector of A and C, and it will be certain that P also has to be part of it. Luckily for us, there's only a single point that is part of both bisectors. This means we found where P is. One quick note though, I've been assuming that there is only and always a single intersection point. It is very obviously true just by looking at the diagram, but obviously is not an acceptable answer in math. Later in the video, I'll actually show examples of cases where multiple intersection points can exist. But for now, the intuition I described with the bisectors should almost be enough to prove that such a point is unique, and I'll leave that as an exercise for the interested viewers. I'll show my solution on screen in 3, 2, 1, if you want to take a look at it, and the solution is hidden again. we now have a way of knowing where exactly the polygon vertices are. For a given 3 neighboring cells, the process that we'll have to follow is first calculating 2 of their sides bisectors, and second finding their unique point in common. Now, I didn't really explain the process in a more formal way with math symbols, allowing us to get the exact formulas for the vertices positions, but I'll show my solution right now in the form of an animation, so you can either look at the pretty symbols move around or pause and ponder over what they actually mean. Now that we know where a single intersection point is, we can repeat the process for every triplet of neighboring cells. Then generating a Voronoi polygon is as easy as getting the list of all its vertices and linking them up together. Except we still need to know in which way to assemble them. To us humans, it is very simple to see which way to link the points, that is, along the cell's boundary, but remember, I'm only showing the colored background to help with clarity. In reality, the computer does not have that information. Thankfully, there is a very simple solution. This might bring back harsh memories of trigonometry to some of you, but don't worry, all this function does is give us the angle a particular vector is pointing to. This is useful as all the points of a Voronoi polygon, correctly ordered, go in a consistent way around the cell's sides. And this property follows from the fact that every Voronoi cell is convex. This means you can trace the polygon's edge by going either clockwise or counterclockwise around the sides, while keeping track of the points in order. Now, I kind of lied when I told you that was all we needed. In fact, there's one last thing I've been using without really explaining how to compute it. It is yet another very simple operation to us humans, but not to computer. Namely, knowing whether 2 cells are neighbors or not. Earlier, I called 2 Voronoi cells neighbors if they shared an edge. I like to see it as how there is a perpendicular bisector between every 2 cells, but part of it is blocked from view or obstructed by other cells. Here, for example, we can see how when I add more cells, they start to obstruct parts of the bisector between A and B, until maybe it becomes fully covered, meaning the 2 cells are no longer neighbors. Let's look more closely at a case with only 3 cells, the simplest case. A and B, in red and green respectively, are the cells we want to check to see if they're neighbors. C, the cell in blue, will try to obstruct the perpendicular bisector that is shown in white. I will show the obstructed parts as a dashed line. For an obstruction to happen, it is easy to see that there has to be an intersection point between the 3 cells. In other cases, C is either too far away to create an obstruction, or in between A and B, which I regard as an edge case in the algorithm. In the case where the intersection point actually exists, it divides the bisector into 2 parts. One part that gets closer to C, and another one that gets farther from it. The section of the line that goes away from C is the part of the edge that is left untouched, unobstructed. We're able to see this in action thanks to the Voronoi diagram in the background. This section of the line is too far from C compared to A and B, and it does not get affected by it, as seen from the fact that the pixels here are not the same color as C. The other side of the bisector is obstructed by C. This is because the points there are closer to C than they are to A and B. In the background render of the complete diagram, we can see here that they're the same color as C, meaning they're indeed closer to it. This is the part of the bisector that we know is obstructed, and we can then remove it from the potential edge between A and B. we have narrowed down the extent of the edge between A and B. Now we just have to repeat this process for all the other cells, possibly chopping down more parts of the bisector. When we are done, we can check whether some non-empty line segment remains, meaning A and B are neighbors, or nothing remains, meaning they're not. And this is the final piece of the puzzle. Almost, since there's still cells we cannot draw, but this is an easy fix. As you can see, the cells on the outside actually stretch infinitely far away. This was not a problem when we were drawing each pixel individually, because we were restricting ourselves to a finite screen, but now we need to artificially limit ourselves to just a small region of the plane. For that, we can introduce a set of borders and compute their intersections with the cells to form the missing polygons' edges on the outside. And we're done. Or at least, we are done with the simplest case of Voronoi diagrams. It is also the most documented one because it is the most useful. Most applications of Voronoi diagrams I could come across only needed this rather simple model. Yet now that we reached this point, I still want to explore further into unknown worlds, twisting reality just to see what such a diagram could have been in another universe. One that is only accessible by bending rules and altering mathematics so as to reach a reality that we cannot truly see. Imaginary numbers, 4D for example, so many things we only theoretically understand, yet they're everywhere and their effects can be used to make our world better, or even create new worlds in video games and movies. Has anyone seen a portal do this in our universe? Has anyone seen anywhere a straight line is not the shortest path between 2 points? Yet if we imagine worlds where these properties held true, then we could use those results to solve real-world problems. That is the idea I want you to keep in mind as I invite you on today's ultimate journey. Pythagoras' theorem. Take a right-angle triangle and the square of the length of its longer side, the hypotenuse, is equal to the sum of the squares of the other two side lengths. That is a mouthful, but it is also one of the most well-known theorems, often the first one formally taught in school to my knowledge. And for good reason, triangles are everywhere. Even where there's no triangle, you can still imagine there is one to take advantage of its numerous properties. For example, take 2 points on a plane. If you want to know the distance between the 2 points, using the Pythagorean theorem is a very good choice in most cases. Imagine a triangle somewhere around here with the ends of its longer side touching both points, and its two other sides along the direction of the axes of the plane. Since the two smaller sides are along the axes, their length can be measured by just looking at them and comparing them to the base. 4 units and 3 units. But because the triangle we imagine has a right angle, we can use the Pythagorean theorem, and applying it gives us the other side length, that is, the distance between the 2 points, which ends up being 5 units in this case. And this Pythagorean relation is the most common way to calculate the distance between 2 points, as this distance is the exact same as the length of the hypotenuse of the triangle. But what if it was not? Who told us that the distance between the 2 points must be this particular line? Who told us it's not this curved line, for example? Now that has to be Euclid, the man who created what is called Euclid's postulates, a set of rules defining intuitive yet hard to prove geometry principles. For example, a straight line segment can be drawn joining any 2 points. Intuitive, yet hard to prove. The world we live in generally abides by those rules, and in this case forms what is known as Euclidean space. But we can imagine other worlds that do not follow the postulates. For example, a world where no straight line segment can be drawn joining any 2 points. Some of these worlds are obviously more interesting than others and have been used by the industry many times, in movies and video games for example, creating structures that mathematically make sense but do not belong to the real world. What I want to focus on in this section of the video is changing the definition of distance. For example, remember how there are squares in the Pythagorean theorem? Yeah, let's get rid of them. The distance calculation we end up with is what's called the Manhattan distance. To see what that does, here's a Voronoi diagram that uses the classic distance computations that I will slowly change into the Manhattan version. See how such a simple change created a totally new diagram? Now that is interesting. Let's try something different. Let's make it so that every side in a Voronoi diagram has an additional attribute called its weight. What this weight will do is, when computing the distance from a point to a site to determine its color for example, the distance will be multiplied by the point's weight. Let's see what this very simple change does to our diagram. Remember this animation? It's the one from the introduction at the very beginning of the video. Do you understand what it means now? This is a glimpse into multiplicative Euclidean geometry. Here, the shortest path between 2 points is not necessarily a straight line, and the cells that were originally made of straight lines now come in all sorts of shapes. That is what we have to deal with now if we still want to create polygons out of those. But do not worry, I'll be your guide in this foreign world with far less online resources and very few people exploring what we'll be discovering today. Let's try to extend the logic we found for regular Voronoi diagrams to ones with weights, called weighted Voronoi diagrams. This is where things got both uncertain and a little more mathy for me, and that was definitely the part that took the longest time to figure out. By now the steps look very straightforward to me, but doing no research definitely got the better of me. The thing is, I originally wanted to render a weighted Voronoi diagram because I needed weight for my specific use case, but I did not really know what a weighted diagram looked like and just went off of intuition. For example, I wrongly assumed that one could just shift the intersection points a bit depending on the cell's weight, but that turned out to not be the case. I had to find a way to deal with circular edges, even if that looked very complicated. And this is where I rediscovered a concept similar to the circles of Apollonius. To understand this specific kind of circle, we first have to understand what a circle is. Really, what is a circle to you? To most people, it is all the points that are at a specific distance to a given point. And you would be correct. For example, the set of all the points that are exactly 2 units away from C is this circle. If we wanted to draw the circle on a sheet of paper, one method we could use is placing a stick that is 2 units long, put one end on C and then rotate it around until it traces the full circle for us. Now something else we could do could be to choose 2 points instead, A and B, and try to make a circle out of them. To do that, we will attach a stick to each of them, of a special kind because they can stretch, and one stick is always twice as long as the other one. The magic happens when we attach their tips together. Now if we try to rotate one of the sticks around, say the blue one, just like we did in the previous example, both sticks will stretch to make sure they keep their end in contact, all while making sure the red stick remains twice as long as the blue one. And now what will happen when, just like with the first example, we draw the path taken by the end of the sticks? It's a circle, but most importantly, if we think of what it's made of, that's all the points that are exactly twice as far from the blue points as they are from the red one. In other words, that is the definition of the boundary between two weighted Voronoi cells, one with a weight that is twice as much as the other one. This circle also has a name in a broader context. It is a circle of Apollonius, a circle defined not by the constant distance to given points, but by a constant ratio of distances to two given points. In this case, the ratio was 2. Each point of the circle was twice as far from one point than to the other. Here the circle is generated by different ratios: 3 to 1, 5 to 2, or even 1 to 1. In this special case, what we end up with is the perpendicular bisector between A and B. If you recall, we saw earlier how that was the boundary between two non-weighted Voronoi cells. Now we can understand that this line is simply a special edge case, and that in its general form the boundary is a circle. In the early example with one stick exactly twice as long as the other, that was for two cells with one weight being twice the other, and the boundary between their respective cells was this exact circle. Again, here's an animation of all the relevant computations for those who are interested. The definition of the boundary between two cells will be transformed into a clean, more usable equation, proving it is a circle along the way. In similar fashion as the first part of the video, the things we need to find now are: first, the vertices of the Voronoi polygons, and second, their edges, or a way to link the vertices in the correct order. Now that we have the expression of the boundaries between the cells, we can do the same as last time, calculating their intersection points to find the vertices of the Voronoi polygons. But also, just like last time, we'll need to determine whether two cells are neighbors or not. So let's clear this up first. It is still possible to use the same reasoning as before here, thinking of two cells as being neighbors if their boundary is not blocked from view by any other cell. It is more complicated than before though, as both cells' boundaries and the bits that get chopped off can take different shapes. But at its core the process stays the same. We start with the full untouched line of sight between two cells, then remove small portions of it as we consider every other cell. Just like last time, it is necessary to add borders to trim the polygon on the outside of the diagram, as some cells diverge as well. Quick note again, there are many small details I'm omitting or very quickly glancing over, but if you're actively studying a relatively similar topic, I encourage you to review my code that I'll link in the description, and that should give you all the necessary details. But with that, we're able to know whether two cells are neighbors and ultimately filter out the polygon's vertices. Now remains finding their edges as well as linking them all together in the right order to form the final Voronoi polygons. This right here was the part that gave me the most trouble, but I think I ended up finding a simple and robust approach. It started with me realizing that a polygon is in reality just a chain of edges. More precisely, a chain that forms a single loop visiting every vertex once. This means that every vertex is in contact with only and exactly 2 edges. So if I manage to find all the individual edges, I could then build the full polygon from all of them, adding every edge one by one into a big connected chain just like Lego bricks. This would also magically work with cells that are split into multiple polygons, which can happen by the way, as we can just repeat the process if we find there are still edges that we have not processed. Finding the edges was also a complex step for me, as I first wanted to rotate in a fixed way around the cell's center, just like we did in the non-weighted case, thinking it would be the easier approach. But since here the cells are not necessarily convex, it was very challenging to find a method that worked. The issue I often ended up facing was linked to the fact that, given 2 points on a circle, there are 2 distinct ways to link them and form an edge, either in one direction or the other. The reason why I faced this problem in the first place is that when building an edge from a weighted polygon, the only information you really have is 2 points and a circle, so basically this configuration. Among all the methods I tried, for some reason they all eventually started using the wrong arc for getting the edge, obviously messing up the polygons. But once I began considering each edge independently with the Lego chain approach, I had to rethink the way I viewed edges and arcs, and the solution clicked for me. Take 2 weighted Voronoi cells and their boundary. We want to figure out how the edge between them looks. We know it has to have ends on both their intersection points, and that it has to follow their Apollonius circle. Therefore there are 2 possible options, and as I showed earlier, this one is correct, and that one is the one we want to avoid. I'll now draw the segment between the 2 sides. Notice how the correct edge always intersects the segments. More precisely, the center of the arc is always inside the segment. We can simply use the one whose midpoint lays inside the segment. So we're able to create edges from just intersection points and Apollonius circles, which is information we already figured out. With this method and everything we found before that, we have done it. We can find the boundary edges as well as the polygons for a multiplicatively weighted Voronoi diagram. And the best part, it still works with regular diagrams. If you recall, they were only an edge case of the more general weighted form, so it makes sense that the method is compatible with them. One last thing, you may be curious as to how I'm able to render these polygons. I mean, they're not really polygons after all, since they contain arcs, that is, edges that are not straight lines. To display them on the screen, I sample multiple points along the arcs to approximate them. Enough sample points really that they approach the true arc to a satisfying degree. But there you have it. This is the end of our journey into understanding Voronoi diagrams to a deeper extent, into putting mathematical wrappers around their properties so that we can use the diagrams in many different applications. And for the second issue I mentioned at the beginning about how rendering Voronoi diagrams was very slow for a computer to do, our final method renders almost 250 times faster than the original. I have to add an asterisk on that one, but all the details are in the repo down below. Now I hope you enjoyed this journey, and I will see you in the next one. I hope you enjoyed. I know that was quite a long ride, and I hope it was worth it. Here's some of my closing thoughts. If you're still here, you might as well stick around. I'm sure you'll find something interesting. This kind of video is really not what I'm used to, so I hope I managed to find the right balance between vulgarization and formality. If you're new here and browse my channel for a bit, wondering why your recommendations showed a bunch of Minecraft content, here's why. I mainly post video games content like Minecraft Redstone, Celeste, Tetris, and this video was more of a one-time thing, so if you want to support me by subscribing, I think you should know that. For my regular viewers, don't worry, I have tons of projects. I just need a little more time to manage school and completing them at the same time. The source code for this video, as well as for the fast Voronoi package, are all in the description, so if you want to check them out, start the repository, you're very much welcome. I don't think I'll be revisiting the library anytime soon, unless I really want to add a feature or two. The time complexity is big O of n cubed, for example, which is not ideal, but if you want to try and optimize the thing, feel free to give it a pull request. I'm just afraid I won't have much time to dedicate to solving similar issues myself. The custom soundtrack I composed for this video can also be found in the description, with a link to my music channel. On the video's code, well, I know it's absolutely horrific, but I just wanted to be done with this project already. Animations with manim and without experience with it are really time consuming. In the description are all the sources I used while writing the script, and I encourage you to give them a read. Especially the polygon characterization article. This paper explains alternate ways to find weighted Voronoi polygons, and the vertex calculation method covered is similar to what I found on my own. I know I insisted on the weighted Voronoi part a lot, even though it's less useful compared to the amount of work you have to put into, at least for my limited amount of research, but I did that for multiple reasons. First, it should help introduce my code a bit better for those who want to try and understand it, and also I think it helps with understanding what Voronoi diagrams really are. For example, it felt really rewarding to me when I understood that perpendicular bisectors were a special kind of circle in this context, and I know how little fun facts like these really help stick abstract concepts into the memory of students. On the time I spent making this video, again, this is not really my strong suit, and I don't really think I'll post more videos of this kind. For my estimations and Waka time, I spent 10 to 15 hours doing research, 70 hours on coding the actual library, 20 hours on the scripts, and 45 hours on making the animations for this video, so in total about 150 hours. And that's not even counting music creation and video editing, which I don't know the time spent at the time of writing the script. Now the last thing I want to do is thank all the people that made this video possible. Thank you to Alexi for support throughout my research and early feedback. To Quentin for creating the gimmick that made me start this journey in the first place. To Grant Sederson and the manim community for creating and maintaining the library I used to create these animations. Thank you to my family for letting me work on this project way too much than I should have. And thank you for watching.